Welcome back to geometry. We want to take a look at section 25. We've already talked a little bit about it, of course, and we've looked at transformations, and we've looked at isometries, or what these things are, and then we also looked at translations, one example of an isometry. And we'd like to continue looking at our examples of isometries by looking at rotations. So a rotation is exactly what you would expect it to be, but it's described by two things. It's described by a point and a degree measure. And what that does for us, or what that tells us, the point is the center. Right, so we say that here's where we're rotating from, and so if we have some line of reference, maybe where a point is, and we're rotating about this point. And when we rotate about that point, how far we're rotating is the degree measure. So the point and degree measure indicate the center of rotation, right? The center of rotation and magnitude of rotation. Excellent. So there may be times, in particular on an exam, and I think maybe even in the homework, in order to perform a rotation, you need two devices. One to measure the angle of rotation, and another to locate the actual point image. So what they mean by that is if we have a center here and we have some point, we're going to consider this line, right, rotate by the given magnitude onto this line, and then we have to mark it on the appropriate location. So the distance should be the same here. So when we rotate it, we should find that the distance from C to P is the same as the distance from C to P prime. Okay, that should make sense for us because C is fixed. So C is C prime, and the distance from C to P is the distance from C prime to P prime. But C is P, so this distance and that distance are the same. Okay, so you would need those two devices. In particular, if we're not given a very convenient angle of rotation, right? So if we're given 45 degrees, if we're given 90 degrees, 180 degrees, 270, these sorts of things, it should be pretty easy for us to calculate, to find those rotations, even without a protractor. But if we're given something like 47.5 degrees, then you may find yourself needing a protractor. I would encourage you to have one. That would be convenient. There is also an activity where you're asked to measure an angle or measure two angles. So a protractor would be a great idea. And then as far as determining distance, right, if you needed that distance to be the same, you could simply draw the circle with this radius, and that would give you, right, this, and then you look for where this line intersects the circle, and that gives you your image. Okay, so that's how we can perform a rotation. It says it's a tedious process here. It's really not that tedious. It's not bad at all. There is a convenient situation. If we have a grid, it does become relatively easy. So if we consider this example, I can rotate the triangle, right, or I can rotate the entire plane 90 degrees clockwise. So what I'm going to do is I'm going to consider this line, and then I'm going to rotate it by 90 degrees. That's not 90 degrees there. Let's try that again. I'd I can rotate it by 90 degrees, and then I'm going to take this point, this distance, and look at where my 90-degree rotation and that distance intersect, right, where the circle and that angle measure intersect. And from that, that gives me my intersection. From this intersection point, I see where my new point should be, which was right there. Now, you don't actually have to go through that particular process to rotate it by 90 degrees. Recognizing that if we take this L, okay, this kind of funny looking L on its side here, and if we rotated that 90 degrees, it would become this guy right here. And that endpoint of the L is the point that we're moving. So what we recognize is this telling us is that down, right, down, the direction of down becomes to the left. And we see that to the left becomes up. And if we continued that investigation, we would find that moving upwards would correspond to moving to the right, and that moving to the right would become moving down. So you don't have to draw all of that stuff. What you can do is you can just observe. Let's see, we've gone down 1, to the left 2, so we're moving to the right 1 and up 2. Excellent. Now there's a bit of counting to do. So I like to count by 2s, makes it go a little bit faster here. So 2, 4, 6, 8, 10. If we wanted to consider this point, we would have to go down, we'd have to move, if this is to the left 10, that means we have to go up 10. So 2, 4, 6, 8, 10. So this point is going to be all the way up at that top line. And then we have to go down, let's see here, 2, 4, so we have to go down 3. So down was to the left, so to the left 3, there's that point. So this is A and this is A prime. If this is B, this is B prime. And then this point here, which is to 4 units up, meaning that it is to 4 units to the right. And it is 2, 4, 6, 7 units to the left, meaning that it is going to be 2, 4, 6, 7 units up. So that gives us this point here. So if that's C, then this is C prime. And again, we can connect these using straight edges. There we go. So I've performed the rotation. All right. So we talked a little bit about this, particular property. I claimed it, or I stated it, as how we can find our rotation of points. But when we consider a rotation of points, the original point and the new point, the image of a point, are the same distance from the point of rotation. So in a rotation, a point and its image are equidistant from the center of rotation. So that would mean that if we have a geometric figure and its image under a rotation, then we could actually find the center. Because if they're equidistant from the center, then the the center must lie on the perpendicular bisector of any point image segment. So when I say point image segment, let's see here. Well, they say it up here. By point image segment for a transformation, we mean a line segment whose endpoints are a point of the original figure and its image under the transformation. So, for example, the line connecting A to A prime is a point image segment. The line connecting B to B prime is a point image segment. Okay. All right. So if we consider the perpendicular bisector of these two lines, where these two intersect will be right at P. This is maybe not the best one to consider. Maybe it would have been better to look at where C, this guy. So if we were to look at that, bam, bisector, perpendicular bisector, and perpendicular bisector. Excellent. So we can look at that in this example. Let's find the center of rotation for these figures. So there's two examples here. Find the center of rotation for this pair and the center of rotation for this pair. Now, if you were completing this on an assignment or on an exam, I would expect you to use a straight edge and a compass to help you identify the perpendicular bisectors and the center of rotation. So I'm going to use a variety of colors here. So I'm going to find or give the point image segment in red, I believe I have. So I'm going to connect these two. And I'd like to connect these two. Now what I'm going to do is I'm going to use green. My apologies for anyone that is red-green colorblind. If we use, let's see, I'm going to zoom in here. I'm going to go ahead and simply, to start, because of how convenient it is for me to move lines, this is certainly not the perpendicular bisector, but I do have a perpendicular line. And then I can go ahead and move it to where I believe the middle is. Excellent. I'll do the same thing for this line over here. That appears to be perpendicular. And then I'll just go ahead and move this to the center. Let's see here. Well, it's somewhere around there anyway. And then what we want to recognize, again, it is the perpendicular bisector, so we know they're perpendicular. And then the line that, or the point that we obtain is the center of rotation. Excellent. So we can do the same thing for this example. Let's go ahead and add our lines. So let's do the point segment lines first. And it's good to pick lines that aren't going to appear to be almost parallel. That's not going to help us out too much. So we want to find lines that are as off from one another as possible. So I'm going to connect this point with that point, and then I'm also going to connect this point with this one. So could I have gotten something better? Possibly a little bit. It looks like maybe if I would have chosen that point and this point, that probably would have been a little bit better for us. And that would have been fine to choose as well. Okay. So it doesn't have to be perfect. Just try not to pick two that are parallel to one another. That would not work out well. So let's see here, find something that is approximately perpendicular or exactly perpendicular when you're working on your homework. and move it to the center, so that way we have our perpendicular bisector. Of course, when you're working on your homework, you should be finding the exact perpendicular bisector, which you are capable of doing based on our discussion of content from section 23. So for our other line, let's see here, find something that is perpendicular. And because of how I'm creating the notes, I'll go ahead and find the center, which I think is maybe here. So I'm going to have to extend that just a little bit. There we go. And that should be pretty close. Anyway, again, when you're working on your homework, you will be able to find exact perpendicular bisectors. So here we have our perpendicular bisectors, and we have the center of rotation. Excellent. So both of these transformations, the ones that we've talked about so far, a translation and a rotation, they preserve what's called orientation. And orientation, there's a couple different ways that we can think about it, but to give a really brief idea here, let's say I have triangle ABC, and let's say I performed a rotation, and that rotation gave me triangle, let's see here, A prime, B prime, and C prime. Then the rotation, the way that I like to think about it is how you travel around the diagram, or travel around the figure. So it doesn't necessarily make sense on like a circle. It doesn't necessarily make sense for a line or an angle. But if we have a figure such as a polygon, then this is a great way to think about orientation. So if we have A, B, C, right, as we travel A, B, C, in that order, we are traveling what we see to be, let's see if I change the color here, right, we find that as we travel along, we're traveling in a clockwise rotation, A, B, C, right? That's clockwise. And as we look at this guy, if we do the same thing, travel A, B, C, right? The images A, B, C, we are still traveling clockwise. Excellent. So we can, that's very convenient for us. If we were to consider maybe, well, let's see here. I'm going to move this down a little bit. If we were to consider a reflection, there we go. If we were to consider a reflection, so let's say that gave us A prime, B prime, and C prime. Actually, let's give it double primes because it's a different mapping. Oops. Well, that's not what I wanted to do. All right, let's try that again. I'm going to move this guy and then take a look at A double prime, B double prime, and C double prime. There we go. So now if I zoom in on this and I consider traveling ABC, I notice that I'm traveling ABC in this direction, counterclockwise. So the orientation you can observe as how you're traveling along a figure. If you end up traveling in the opposite direction, you have opposite orientation. So for a figure with this particular orientation, when we reflect it, we have an opposite orientation. When we rotate it, we have the same orientation. So the isometries that we've considered so far, translation and rotation, both preserve orientation. Excellent. So for now, that's all that I wanted to share, and we will move on to reflections and glide reflections in the next videos. So I'll see you guys again shortly.